So in a purely turbulent and chaotic way, I'll just start saying and writing something, and then people can interrupt me at any moment, or just wait until I make a, a break in it. So, yeah. Just personally, I recently realized that there is a classical problem for which I don't know anything. And it's a problem of turbulence and boundary layers, channel flow, and all this, which is kind of infinitely more important than isotropic Kolmogorov turbulence. And so I thought that it's kind of Prank, Karman, great people, they did everything. And then I opened books, and there's just nothing there, basically. So then I started looking. What does that mean? What does it mean? So what do we know? Let's say we have a plane flow with whatever profile. Mean flow, there is a profile plus fluctuation. We have some fluctuations of vertical velocity and some fluctuation of this. Let's say we are in 3D. Okay? This profile could be whatever, but we say, okay, let's consider a particular case we have a wall. Then there are arguments which, in between wishful thinking and religious belief, that this profile is logarithm of y. Good. And I mean, it's a great result. It seems that experiments are pretty close to it. It's a pity that they did not get a Nobel Prize for it. Still, it's not a proof. It's kind of, if there is an overlap between viscous region and the central part, let's say, it's in the pipe, then it will be logarithm. There are 3 types of arguments, and they all are hand-waving arguments of the same type. We get 5/3 in 3D, and 5/3 is wrong. Okay? So this is the same type of argument as 5/3. Good, okay, even if it's true, I mean, let's say, what we can say about U squared average as a... Yeah. What can we say about U squared average as a function of y, V squared average as a function of y, but UV, which is a momentum flux, which would naively be just constant, if we don't, or pressure gradient, if we have a pressure gradient, and W squared is a, just, I mean, simple questions. Well, there are huge books, so I mean, like, I don't know, you go to the library, there are 10 books on boundary layers. 8 of them say nothing about it, and 2 of them say, well, it's probably y independent. Then you look at experiments, they're very strongly y dependent. And different experiments not exactly very similar. Okay, the standard argument was like this, that if you look at this, let's say, time derivative of anything like U squared, you will have the energy production, apart from other term, you will have energy flux term, and you will have energy production term, which will be du dy, well, with a minus, uv. Okay? So the argument was that because we expect this to be y independent, and this to be 1 over y, then energy production is like 1 over y. And so, because we say that we would kind of think the following way, that on the distance from the wall y, we'll have vortices of the size y. And so energy production must be typical u cube, not mean u, fluctuating u, divided over a typical scale, which is y. So because it's already like 1 over y, this is epsilon of y, so that probably u cube is kind of constant. Then there was this idea of Townsend, which is again some kind of very nice hand waving, saying, well, you know, of course there are vortices like this. There are also vortices like that. And at every size there are vortices which kind of contribute, or vortices which are attached to the wall, but can go to this, and then they can go to this height, then they can go to this height. Or there are vortices which are like this, in a plane. What prevents, and this distance y, vortex in a plane exists, which is much larger than y. It gives no contribution into the momentum flux. Townsend calls it passive modes. It's passive. Do not contribute into the momentum flux vertically, but they definitely contribute into turbulence on this level. Then I ask myself, so what? Is there an inverse cascade? So at a distance y, I have this input into the from this that much of energy goes from the mean flow to turbulence. Then what? It all dissipated by viscosity at this level. What happens? Or some of it goes to even larger scale by inverse cascade, like what we see with shots. We see this, or Dario, what you see. Okay, so you have this layer. So imagine that this is your layer. Okay, now in this layer, nobody says that you cannot get energy into these big nodes. So maybe they will have unbounded layers. They say, yes, well, maybe. They start numerics. It seemed to be some kind of maybe. And then those quantities start to depend on y. And I did not even start asking about structure of turbulence. It's all about single point. All single point moments, there is no idea, no theory, no even meaningful.
It's not really a single point because it's a distance from a very specific type,
No,
the boundary.
This all are single.
Yeah, but I mean, they're single with reference of the distance to a place where actually
They are point dependent.
Yeah, I understand.
But they are not two-point correlation function. Because
I
the moment,
understand. Yes, you're right.
because the moment I'm starting asking what is V1 U2,
yeah.
I can write an equation for it. I already studied on it a couple of months. That's a completely different story. Then you ask actually the following thing: how the flux in space coexist with the flux in Fourier space? Because what happens in any such situation, you have an inhomogeneous flow, which means that in this case, your turbulence level potentially could be different. Okay? And now what Dvina now does, I think, very interesting numerics is this Kolmogorov flow, which there's no boundaries, which means that this profile could be different. And now, surprisingly, all this is related to this problem of condensate, which we study in a completely different context. Namely, that if we have this inverse cascade in 2D, we create a huge vortex. Okay? So we create this huge vortex, and then we have a turbulence which exists inside of this vortex. But it's the same problem. Just the geometry is different. But then again, you can have a box which has an aspect ratio larger than unity, and you can have plane flow into the zonal flow. So your condensate would be not a vortex, not a dipole, but a zonal flow. Again, the same question you ask. You have U mean profile as a function of radius. You have turbulence inside. Now, I can prove that momentum flux here, just the fact that the all momentum goes to the wall, tells you that this energy production is positive, which means energy goes from the mean flow to the turbulence. Here, you make very mild assumption about this profile, and you understand that the energy goes from turbulence to the mean profile. Good, that's what we expect in 2D. Then again, the same question, what is this profile? There is a sketch of a theory, and we're working now on it. And then again, what would be, U squared, mean value as a function of y. And how, again, here, we know that in 2D that would be an inverse energy cascade. But how it coexists with a special energy flux.
But you have to have boundaries there.
Here I have boundaries because this vortex always lives in the boundary. It's a condensate. It does not exist in an infinite space. For the good reason, it's actually diverges. It always exists in a box.
Mm-hmm.
Now,
what kind of boundary? Not where, but what kind of boundary conditions?
Now, when we try to find this profile, we try it very far from boundaries. We don't know how it works in the boundaries.
Yeah.
Experimentally, when we look at it, we see that it's very non-trivial situation. If it's vortex that goes like this, then here we have this lubricant vortices, and we need them. I mean, they really kind of need it over here. Moreover, there is, something about this vortex which, at least the way the theory is now, this vortex must be not completely, it must have this type of fluctuation. This is why we're so interested in the fluctuation of axially symmetric vortex. It's important. In a purely axially symmetric situation, nothing happens. So what I'm saying is that, in a sense, this problem and that problem, they are problem of a very similar kind. I have a mean flow of a most simple geometrical nature. It's either plane flow, depends, either shear, it's not constant shear, but it's kind of shear. It's plane flow depending on one coordinate. Here is the same. I have one component of mean velocity depending only on one coordinate in space, and I'm asking what happens to turbulence. And people who did unbelievable amount of numerics and experiments cannot answer simple questions because they never asked them. What actually is the profile of this? What is profile of this? They checked some kind of basic things about, I don't know, degree of anisotropy, what is the ratio of this to this. It's all behaved very strangely. And in a boundary layer, because of logarithm, everything converges very slowly. And because it's very slowly, then it's difficult to build in. So what I just wanted to say is that somehow, you know, I discovered that people, great people who derived this, did it before Kolmogorov did 5 theory. And then they died. And nobody, well, everyone died, but I mean, it's just, you know, it was very useful to read this book on turbulence history that we wrote, because at last I understand what happens when and why. Actually, nobody knows what is the structure of turbulence in the boundary layer, because people who did, you know, mean profile series, they did not know Kolmogorov. When they learned how Prandtl derived Kolmogorov, just a few months left before he died, and then after that, nobody actually tried, not that they found any trace of developing even any type of theory along Kolmogorov, you know, about turbulence, not about mean profile, because it's all self-consistent must be at the end.
Correct me if I'm wrong, I thought this multi-point correlation was looked by Jan.
No, in Yablon book, if you look, you look at some very non-trivial correlation like V, P, or I don't know. And this kind of was very nice. It's really what in Morning Yablon is one element which is missing here is that this is a pumping of energy which goes only to the U square. And then energy is getting redistributed between different components via the pressure. Because totally pressure does no work. But it can redistribute energy. Pressure actually restores isotropy, what it tries to do. So there is some other, nobody measured by the way, this is just theoretical argument. But for different point, you can say, okay, we expect that maybe there is some kind of a Kolmogorov turbulence. Not at all evident. Because now you have a very anisotropic situation, and again, you may have something like an inverse cascade. Because nobody says, because potentially, when you're at this distance y from the wall, nobody says that all motions here have the scales which are less than y. No, only motions that participate in a vertical exchange. They have the scale less than y. There are other modes which are playing. And Townsend apparently looking at his experimental data understood this intuitively, but nobody tried to do any theory or any quantitative measurements. Now it's kind of start to appear that there may be indeed this really not constant but logarithmic, and then you ask, okay, if this non-constant, maybe it would influence by this logarithm, which was obtained assuming that they're constant. Say, well, maybe. So it's what I'm saying is that now with a super pipe and with improved computers and with all this old classical problem is of enormous engineering importance and of high fundamental interest. It's very closely related to all this stuff with vortices in geophysical system and other stuff. Namely, you have a coherent flow and turbulence on it. First question, what happens to energy flux in space? Second, what happens to energy flux in k-space? It's now tensor. It's, or at least vector, if you're talking about energy, it's a vector that has 3 components, or include dimension, it has 2 components. And they absolutely, surely different, okay, in Fourier space. It's not like you had only one component which was in the isotropic case along the modulus of k. So I think that this is something which, well, kind of neglected by people who were really interested in fundamentals of turbulence for quite some time. Because we were sourcing out some kind of fundamental things, but this is now, and it came from different perspective, from channel layer boundary and from condensate into D or geophysics or all the zonal flows and plasma. So, but basically it's about coherence and fluctuations at the same time. Okay? So this is the first subject that I wanted to suggest. Huh?
Well, long history.
Yeah, many people must have worked on
No,
it.
they've worked on it. All he's saying is he's not satisfied with the work they've produced and they haven't looked at fluctuating quantities.
I mean,
Yes, this is-
Barenblatt suggested that it's not a logarithm, it's a power law
That's
with an
what I
exponent,
I
which
remember.
is a kind of, It's another dream. I mean, I have a dream. So
Well, we had
I will have a dream that it's logarithm, and another has a dream that it's a power which depends on Reynolds number. Okay, a good dream. I mean, it's possible. Well, who knows? And everything was happened after that was looking at the data, and data definitely, and probably for foreseeable future, you can argue whether they're best described by this or best described by that. Okay? But it's, at least in 2D, in this case, it seems to be a way to get this profile self-consistently with the fluctuations, with the way to
I leave not in protest,
Yeah, but I saw that you made me go.
but for other reasons. Triple deck theory. Stephen Cowley.
What?
Triple deck theory.
Triple deck theory.
Triple deck theory.
Yeah.
Can you write it down so that we'll have it
Oh, yes.
for posterity somewhere? You mean this is answer all my questions?
Pretty much.
Good.
Yeah.
Yeah.
That's why I asked.
So Uriel knows what it is, he can tell us.
It is a very fiddly
And who
problem
did it?
in matched asymptotics because you have elliptic parabolic coupling.
It's a real nightmare.
And it's a nightmare, but it's motivated entirely by this problem, and
Ah,
it's
yeah.
a very rigorous and difficult area.
It's a formalism which derives if assumptions are correct. There's much asymptotics which derives if assumptions are correct. Yeah, but I mean, just don't want to keep you. Well, I don't know, this is probably technique, Uriel.
Uriel, tell us what is triple deck
No, I
theory.
knew it 20 years ago, but I didn't forgot that. It's a real mess.
That's, I guess it's probably much asymptotic. You can derive logarithmic law assuming that there is overlap between asymptotics, one of which is viscous and goes from the wall, and another is completely inviscid and goes from the center of the pipe. If they have an overlap region, that in this overlap region it's only logarithm works because then that's it. But that's the idea. And then you can invent technique which actually matches asymptotics for many words. But it's not a point how to do technique. I mean, the point is whether it's true, and I'm not sure. Particularly if it could be, modified by some kind of other logarithm. So that's what I actually want to say is that. And well, we discussed it with Srini, and Srini says that one can argue about Kolmogorov, whether it's a Nobel Prize level work, but I mean, this is a Nobel Prize level work, and it's still a Nobel Prize level problem, and if, engineering level is just so. And really, it's something that, for example, what is the analog of 4/5 law in this case? 4/5 law.
Provided the Nobel Committee increases the money amount.
Yeah, you do this, and engineers will make you rich, so you would not need a Nobel Prize. You can establish your own prize. But, for example, nobody knows if there is any analog of 4/5 law in this case, or in this 2D. Okay? So what is it? Is there any relation on a triple moment of velocity, like it is in isotropic difference?
But now you are talking about momentum flux.
No, momentum flux is this UV.
Yes.
Yeah?
No,
No, I'm talking about spectral energy flux. Because if I can locally get a region which locally could be considered as almost isotropic up to this scale, and turbulent, and then I say that, okay, there must be energy flux towards viscosity, and then delta U cube is equal to 4/5 epsilon r. Is it true here? Or anisotropic completely
Let's see
cube?
very sharp. Let me have a dream. I mean, a lot of our favorite tools have become useless when we are inhomogeneous, we have boundaries, etc. Can one imagine that just like quasi-periodic, quasi-crystalline states can be viewed as projected sections of higher dimensional problems which have normal periodicity or things like that, crystal and normal Ave regularity, Is there any hope that certain inhomogeneous problem with or without boundaries can be viewed as projection of problems in higher dimension with the inhomogeneous or from curved space or anything?
No, curved space is basically uniform. I mean, this space in which you don't.
Uniform and non-uniform.
Well, you can impose non-uniformity. Well, I mean, in a sense, you may say that. I mean, look, in this boundary layer, if I look at this as a distance y, but then I consider here the distance between points which are much less than y. Then you will say, okay, I have inhomogeneity, but this inhomogeneity is on the scale of y and it's slow comparing to this distance. So here I would expect this delta v cube to be minus 4/5 epsilon r. Yes or no, I mean?
Yes, of course. Maybe with some small correction, no?
Not that anybody, not that anybody but
Not that what? Anybody ever measured?
there are a few questions here.
Epsilon maybe
Yes,
depends on y.
Yeah, well, epsilon does depend on y, but now the question is, epsilon, it is this, even if it's linear function of distance,
Yeah.
which is not guaranteed, because as you go towards r, you changes your ratio of your scale with respect to your distance, which is your degree of inhomogeneity. So in a sense, you go towards the cascade and you think that it's getting more isotropic. There is another question. Even if it's linear without, what is this epsilon? Like what Dario did. Is all epsilon went down this cascade, or part of it went up? Because it's still a finite ratio of this to this, and you can get your energy into this mode. You don't need to put all the energy into smaller scales. You
So,
see?
but
And if it leaks a little bit over there, then you can.
So the ideology of the 4/5 law that it applies in reality in turbulence is that whatever inhomogeneous, I'm paraphrasing what I learned from Maria, whatever inhomogeneities created the flow, they are not present on small scales. So by that argument, if I take it for this particular case, then you should have 4/5 law, as you say.
And this is,
This is small enough.
And
Maybe with some corrections.
and this is another nice dream, which may be true and may be not, or it may be true in some cases.
People are
So, but if it's not true, it means that actually that isotropic turbulence would not be relevant for this
Depends on
boundary
what.
flow.
Imagine that you have a large scale whatever
And
mass.
then there would be
And then
disaster
you
for
look at the
turbulence.
small scale, of course it is inside this mass, but if I average long enough, but here I have a very peculiar situation. I have a persistent flow in one direction, with a profile in another direction, and in this flow, and I consider it, stationary, like going forever. And what we learn that in these layers, if you wait long enough, you start creating these big plane vortices, which do not participate in the moment transfer, but they do participate in the energy balance. And they completely, in principle, would screw up all your idea of local turbulence at this distance of the scale. That all the energy at this distance would go into viscosity at this distance. Why not? If some energy goes into a larger vortex, and this vortex then turn like this, nobody says that vortex must live like this. You create a large vortex and turn like this and bring this energy here. You see? And also start participating in momentum transfer. And it's about formulas too, which means that there are some, maybe logarithm, or maybe some other function which is completely missing here. There is a phenomenological picture of Townsend. It says that there are a hierarchy of such vortices equally distributed, and they would give you extra logarithmic dependence. And then nobody thought over whether it would somehow influence the other things. They are inactive, so they probably do not influence, the logarithmic profile. So it's cool.
So what you're saying now is that for this scenario, there is not only the cascade, the Kolmogorov cascade. There is also some other energy transfer by the vortices created like this, turning like this, and going crazy.
So in a sense, no one says that energy which is, the standard idea is that at a given distance, you input energy on this scale. This is the scale in which you input energy. All this energy inputted on this goes into viscosity as this way. You ask, what is the correlation function, which I omitted here, which is V, it's a vertical velocity, P, it's a dy, okay, plus V total square over 2. This is the flux of energy in vertical direction. Silently, without much argument, it's put 0 in most books. Again, why? And then again,
But then the
Because
choice,
you need a
so that you're looking for some
Ah,
big
You need a
deviation.
closure, it's not
Yeah,
linear
he's
equation,
looking-
so you must close
Look
at
at,
some point.
he's
You never
looking
solve
for,
it
he's
exactly.
looking for a big deviation from cascade theory, so then you should be looking for an even bigger one. What would be the extreme example where there should be a cascade, but in fact there's not? Because there's a bypass of the cascade.
Yeah,
Entirely.
what Christoph did not tell you yesterday is that with this curved space, it's actually, when you go
Yeah?
very large scales, that it's actually not a cascade, that it's something which is like growing some kind of a very peculiar mode. No, here I don't think it's very dramatic, but what I'm saying is that here there are things which we don't understand the structure of turbulence in a homogeneous flow completely. Some things which we believe, which may be right, some things which we believe which may be wrong. Nobody actually tried to say what would be, we have in 2D, we have delta V cube equal to plus epsilon r for sure. Here we have minus 4/5 epsilon r. Okay, now we have 3D in the channel flow, or we have 2D inside vortex. Whether these two relations are modified in this case and in this case, nobody knows. We should, by the way, and it's kind of some things which are doable numerically, experimentally.
You can write the equivalent of the 4/5 law, taking into account the fact that it's not.
No, not
You have an extra, the book of Inns is done,
Yeah.
and you have an extra,
I can say
variable
delta
that
V
is-
cube is equal to epsilon 4/5 epsilon as a function of y times r. Okay, R12. Good. Now this R12 is in x direction, in y direction, or in this other direction. It will be the same. We assume, okay, it's kind of getting more isotropic. Now you look at their experimental data. I mean, really, when you look at spectra, there are some spectral measurements. They even kind of not very far from 5 Whether they are isotropic? Well, they're getting a little bit more isotropic as you
Depends
go.
where you are. If you're in the middle of the channel, you are pretty isotropic. If you're close to the wall,
If you're in the middle of a channel, then all this is non-existent, because in the middle of a channel, it's really pretty much a uniform profile. We're interested whether there is substantial gradient. The du, dy, it's a function.
I think what I noticed people, at least in numerics, did in the past, out of the mean profile, you define a shear, right? You have the shear. Out of the shear, you have a shear length. It's just the ratio of the shear to the energy dissipation to some power, I don't remember. Just dimensional analysis. And then you have this shear length, which depends from the distance from the wall. Because if you are very close to the wall, the shear is big, shear length is very small. If you are in the center, shear is 0, shear length is infinite. Right? And then people in the numerics, what they did are the, let's say, scaling law, for instance, the velocity increments, as a function of scale. What they saw is that if the scale is smaller than the local shear length, they see a pretty good Kolmogorov cascade regime. If the distance is larger than the local shear length, then they are completely overwhelmed by anisotropy, and they see a different slope, and then start the discussion.
And it looked pretty decent.
So
when you said
it's very well in fitting with
it looked pretty decent as you work with numerics, where you have 3 points for less than shear and 3 points for larger than shear. And you see what kind of work. When you have like 20 points in experiment, it works much worse. It also kind of works in the sense that you go towards smaller scales and it seems like a more isotropic turbulence. Then again, accuracy is very far from saying indeed whether this energy goes there or part of this energy. It's most likely if you look at certain moment. Nobody was going to look at certain moment. Nobody look at certain moment. It was all looking about spectra. Okay?
No.
And
No. Erik Lindborg looked at the
lot of
third
people
moment
look at
in these geostrophic flows,
Yeah,
which
also
is
the
flows
shadow
which is outside the
Yeah,
Earth,
yeah. Well, no, I mean in the super pipe. I mean really huge
Super pipe.
generous number measurements, or in Australian data or in American data. No, they didn't.
No,
In
Raoul wants to say
No, I
something.
was
Mr. Polak.
suggesting that in the interest of covering turbulence homogeneously, we change the topic a bit.
that's
No,
what I
I'm not
suggested
so-
already twice.
Okay, so I have a not a statement. I have a question for Uriel, which is that he and some of his collaborators have been pushing high resolution simulations and suggesting that we can get much better results if we say go from double to quadruple precision. So far, they have done it for things like burgers, which is deterministic. What is your prognosis for such simulations in things which generate their own turbulence or are stochastically forced?
I mean, the problem is that if you have, in a random problem, if you calculate things by ensemble averaging,
Yes.
you will have Monte Carlo noise.
Mm-hmm.
And that's a real killer because that will introduce a noise that is far exceeding what you have in double precision. So you have to find a clever way of avoiding that.
Yes.
Which could be by just in the case of periodic boundaries, you can integrate with the space rather than average. But there's an idea missing there.
Maybe Sergey, you now responsible for wave turbulence. Just, you know.
What do you mean?
No,
Yes.
we put responsibility on you. So, what is the, problem of? Is there anything exciting, kind of new, and as an unsolved problem of wave turbulence now? What you will see the most important?
Well, I kind of recently came across, I think, interesting subset of problems is when actually waves are in bounded domains, and then resonances happen. The resonant interaction is restricted, and often in such a way that exact resonances happen only among finite sets of modes. But these so-called clusters, can be rather big. So it could be, like, say, a cluster that is contained of 100 triads. And what do we expect to behave in a system like that? I mean, and by the way, when I say resonant interaction, it doesn't mean it's weakly nonlinear equations. It's actually completely strongly nonlinear equations because of the exact resonance, linear terms drop out completely. So it's a strongly nonlinear system. It's basically a system, well, all of you know equation for a single triad, but now imagine have many of them and they're coupled, more degrees of freedom. So what do you expect for a kind of dynamical system like that? I mean, questions to ask. I mean, do you expect thermalization or if you do, does it always
you
happen?
pump the system, why would you expect?
Suppose you don't pump. Suppose you put energy.
Some energy.
Yes. And how will it depend? Whether this property of thermalization will depend on the topology of the cluster. How cluster can have a lot of connections or have very few connections. I mean, it can come back onto itself with connections. So.
Does it look like universal problem, or it may be just a set of different zoo, because you're talking about graphs, okay? So you kind of put the graphs and you get stuck and just isn't distributed.
It's kind of interesting relation to graph coloring problem. That I like to find say integrals of motion in this system. But also it also relates to these decimated systems that you're really talking about. I mean, you imagine resonance, being in resonance is a rule of selecting of the modes in Fourier space that you leave, and the rest you throw away. Okay, so in some sense, it's also kind of like pruned Fourier space.
Yeah.
So that would kind of I'm excited about right now.
I have another question, which is partly related to wave turbulence. Since there are so many practitioners of superfluid turbulence here, there are lots of simulations with Gross-Pidersky, lots of simulations with Biot-Savart, and then there are simulations in which Gross-Pidersky people add some form of dissipation, some people use hyperviscosity, some people use sharp cutoffs. And then immediately they compare with experiments which are done with a real superfluid at some finite temperature. But rarely do I see simulations with a two-fluid model, with a superfluid and a normal fluid, where there is a, honest physical way of energy dissipation. So, what is the considered opinion of all the experts here on the dissipation schemes employed in Gross-Pitayevsky and then comparison with experiments?
I don't know, I can just say that, experimentally, especially in helium, you have an intrinsic length scale in superfluid, which is the healing length,
Yes.
and which in helium is of atomic size, of order of the angstrom. And a typical experiment in helium has a flow cell that has, I don't know, a few centimeters.
Yes.
So there is no way that this kind of a scale ratio is going to be reached in any kind of numerical simulation, be it with Gross-Pitayevsky or with phenomenological models. So anyway, the simulation is far, far, far away from the regime we have in experiments. So in this situation, what people do is put some dissipation mechanism if needed.
If needed means just to attain a statistical steady state.
For instance, or according to the purpose of the simulation they are performing.
Yeah, I'd like also to add to that. I think it's what Uriel said today about Orzak, who realized that sponging is necessary in turbulence computations in order to avoid, the artificial accumulation of energy at the maximum wave number. If you're talking about spectral methods, right? So absolutely the same applies to Gross-Pitayevsky. It's paradoxically, but it's not paradoxically, of course, for people who compute turbulence, that maybe it might sound paradoxical for people who don't know. That in order to compute an inviscid system, you need to have dissipation.
Yes.
In order to be closer to inviscid dynamics, you better introduce some sort of hyperviscosity.
Mm-hmm.
Or you need to have very precise initial data.
Yeah. But also, there is another issue that is specific for Gross-Pitayevsky. Is actually Gross-Pitayevsky does not work all the way to high momenta. At some point, the occupation number is of order 1, and then you have a transition to Boltzmann-free gas. Okay.
Well, that's
so
contained in the stabilization.
and yes, and in terms of Bose-Einstein distribution, it's where Rayleigh-Jeans part of distribution goes into Maxwell-Boltzmann, which is exponentially decaying. But because Maxwell-Boltzmann exponentially decaying, it's like a cutoff. So from this point of view, simulation of Gross-Pitayevsky with cutoff is kind of makes sense, because you're like saying, okay, at some high momenta, actually, occupation number is of order 1, and you will have to somehow model a cutoff. The bad news is that this cutoff is actually not fixed. It depends on temperature and number of particles in the system, right? So it's whereas in spectral methods, it's always a fixed number. So I don't know how one can overcome that.
So, Prishad, do you have a favorite dissipation mechanism in Gross-Pitayevsky?
Yes, but for me, Gross-Pitayevsky is about classical optical turbulence or waves on the water, where we always have, or plasma waves where we have Landau damping. So that we just, it's very, light heart we put growing with large K. And I was never interested much in the direct cascade in Gross-Pitayevsky, because it's kind of trivial. Well, inverse cascade is very important. For me, it's very interesting.
Well, it might be trivial, but lots of people have different answers in the trade.
It's kind of, it's trivial in the sense that I don't expect anything qualitatively unexpected there. But with an inverse cascade, the disappearance of condensate, the vortices, that what Sergei shown, that how vortices appear, then they die, how they annihilate into D or create, or this vortex. So this is very interesting. And it's something where potentially absolutely new phenomena could be found. The transitions to the states which we don't even foresee. So I never really put much thought into large K. But I mean, a lot of people do it.
No, no, I know. I read their papers because I don't understand them. That's why I thought it was a good place to ask.
Druba, what was your initial idea about this? Wasn't it 10 years ago the Crichton problem was on the agenda and it's been solved? What's the next big problem of a theoretical nature,
I
right?
think Grisha did.
Yeah, Grisha,
Something
but
like
it
that.
has a flavor which is too practical for most people here.
What I'm trying to show is that it's actually fundamental.
No, it's not too practical. Actually, I've been saying the same thing as Grisha for many years, and
Just more difficult.
This is one of the reasons that Itamar started working on this thing, because he asked me 10 years ago or so, what are the two challenging problems in turbulence? And these are very, very hard problems, and they're interesting. But I've been thinking about them for at least 25 years, and no worthwhile idea.
In a sense, what's interesting is some kind of a general framework on which we can discuss geophysics, all the zonal flows, these vortices, channel flows. There is a single component which is common for them, namely locally anisotropic flow and turbulence inside it. Are there any general things apart from which direction goes momentum and which direction goes energy? Well, this we can answer, more or less. Now the next question, what will be the structure of turbulence inside, how it determines the profile of turbulence, of mean flow. Frank and Karman did not know anything about turbulence inside, and they determined mean flow is some kind of flow. There are three different arguments. Now, when we try to do it for this, somehow we discover that we really need to, there's no way to determine profile without determining how turbulence actually behaves. Okay? And it's fundamental, I don't think it's...
What we would need is some kind of model, a clever model that would be academic from the engineering point of view, but which would constitute some bridge between this and something which is perhaps doable by very clever people.
You mean Crichton model for
Not like
homogeneous
Crichton
curves?
model for it, right? It could be indeed that we can take this profile somehow, imposing it. Might be that what Guido does, and I actually like it very much, is just it's a Kolmogorov flow. What is nice here is that there are no boundaries.
Yes, of course.
So you have the forcing, which is just sine ky.
Yeah,
Okay?
yeah.
Then you, which means that, then you discover that the U mean profile is just follows this, is also sine ky. And then you discover that UV, this momentum transfer, is a cosine of ky. Good, I mean, now no boundaries, and it's kind of, it's like this, which means that over here U is 0, but the shear is maximal. Again, so you, on the scale of this, you go from shear scale 0 to shear scale infinity. Here is practically must be like isotropic turbulence. Here it's extremely anisotropic. But for God's sake, they interact with each other, they exchange energy.
There are some non-trivial theories. For example, Nepomniachtchi a long time ago developed a Cahn-Hilliard asymptotic for
for this one.
Yeah.
For non-linear, that's interesting.
Yeah,
I never heard.
what Sinai and Meshalkin, I believe, studied was the
Arnold and Michel.
linear stability.
No, Sinai.
Linear,
Sinai.
Linear stability of that
Yeah.
flow.
Yes.
Yeah. And then Nepomniachtchi extended it to the mildly nonlinear thing and found that well, call it the normal form or whatever, is a Cahn-Hilliard equation. And
For perturbation, when I just
That is the perturbation.
I have this flow.
What is it, square root 2 plus epsilon or something like that. Or, it goes unstable at Reynolds number, which is what is it, square root of 2 or 1 over square root of 2 and something. Okay? Yeah. And just above you have this thing. it's a highly anisotropic regime, of course, yeah.
There were experiments with that too, you know,
What we can learn from this experiments also low Reynolds number type, well, not very high.
No, high Reynolds number, Должанский.
Yeah, because what I'm saying, okay, it's what we can learn for, can we learn anything useful for it for high Reynolds number regime? Because of course, I'm asking about
We did
high
a lot of
Reynolds number.
simulations, and Zoom, for example, this will show. We did a lot of simulation of this much higher Reynolds number and tried to develop some theory, but it was semi-phenomenological.
On Kolmogorov flow, yeah?
Can I ask you a question? In what sense is this flow different from, let's say, mixing layer, which will please our engineer colleagues much more?
It is it's much more like a mixing layer than a boundary.
Yes.
Yes.
So why not do mixing layers then? I mean, why?
Here we know the
idea was to have
profile.
an idealized
Here we know
model.
the profile.
Well, you replace the sign by a tangent and you have
Anything.
But Grisha, it doesn't stay a profile like that. It develops vortices, round vortices.
No.
After
I mean,
instability.
this is a
Kolmogorov
mean
flow.
profile. I mean, the velocity is highly turbulent. It's a highly turbulent state.
Look, you know,
But what-
it's you have mean
don't control
profile,
the
right?
factor.
But if you look at two-dimensional picture, it's a vortex.
Factor is an equation. What is the prefab? No, okay. What Guido claims is that for sufficiently high Reynolds number, the profile, the mean velocity is like this. This is a u mean value, and it's like this. What Lucas said correctly is that the $500,000 it's still a kind of what is a factor here and what is a factor here.
It would be wide
Because it would give you a drag factor for this flow.
Grisha, it won't stay only y-dimensional. You know, it will.
The mean profile, yes.
The
Mean
yeah.
profile
profile,
stay
sure.
like this. And the claim is,
It
which
will be
I'm,
convective cells, the vortices like that.
No, but the mean profile is going to be that one, by definition.
Oh, you mean mean average over x?
average over
Average
time.
on the plane, on the
All over
homogeneous
x,
plane. Yeah, sure.
all over time. It's actually over time because everything moves. And then there is turbulence on which not much is known.
But in the past, what we did is to make a mega simulation of the Kolmogorov flow, plus a random phase, such as we recover even homogeneity, plus a random phase in the force. So you are anisotropic, but the random phase shuffle.
You change the direction of your random flow.
No, the direction is the same, but I change the phase. So
you move it up and down.
Yeah, such as you recover homogeneity.
But I mean,
Then
it's
becomes
usually made with periodic boundary condition and on the box size mode. So you cannot.
Sure.
You still can move it around. Yeah.
So you are fully homogeneous. You can do it in a periodic box.
Maybe if we do it in a white noise type, we'll get a Crichton type model
For the force.
No. For the forcing, mean profile would respond with its own time. Yeah.
Of course we did.
But guys, I mean, it makes no sense to talk about mean profile. I mean, two-dimensionally it will be large-scale structures.
What do you mean?
It will be vortex tree, like Harman vortex tree. So your one-dimensional shear flow will break into vortex tree.
It's not one dimensional, it's a forcing which is sinus, and then it will be a mean flow which will be the same sinus. And when you make a snapshot, it will be God knows what. When you make another snapshot, it will be again God knows what. But when you average, you'll get the mean flow. No, I mean just by symmetry.
I'll show you.
Huh? Or you'll
I'll
show.
show you pictures.
Okay. Any more suggestions?
Except going to biology like Massimo, and cosmology, real one,
No.
or economy.
Doesn't make any sense.
Yeah,
Economy is not a safe field now to go.
that's true. But you must risk something.
You know, Sasha Migdal, with whom we were doing the first variants of this.
He's back in town?
Theoretical physics.
He's back?
He just wrote paper on theoretical physics. Apparently, back from Wall Street.
Is that so?
Well, he's still rich. I mean, it's not that he's meet his professor's salary, but.
He resigned his position.
No, he just wrote a paper on.
He just wrote one thing.
I guess two probably, the logical formula. At least, conformal field theory. So, they come back to us, not us.
That's not a good sign.
For physics or for Wall Street?
For the world.
Okay.
Christoph, can't
Yeah.
you say something? I mean,
No.
About two
no.
I am his spokesman.
He only speaks about problems he has solved. He doesn't put a half
Christoph learns from Uriel what problems to solve. That's a lesson of past, right, Christoph? You learned from Uriel which problem to solve.
Yeah.
And not telling Uriel other way around. It's one-way street. But I mean, this always seems kind of strange and interesting. But you know, we do turbulence, but it's just fluid mechanics when it comes to space, also very interesting. Just the fact that you don't have Galilean invariance, which means that any uniform flow is actually accelerated flow. Which we know, I mean, we live on the curve. Space. But I'm not sure that we kind of appreciate, particularly if it's with negative curvature.
But I mean, we live in a space.
We live in the positive curvature. That,
No,
I mean,
yeah.
on the Earth is positive curvature, and it's also interesting, you know. We have this Coriolis force, we have all this, you know, rivers bend in this way, and all this. But when I started to work with Christoph on this, I just enormously enjoyed just thinking how fluid would flow, you know, in this negative curvature space. So sometimes, that's what, you know, people do in statistical physics, in field theory, is you try to take a problem and kind of bend it. You know, just look what you, which is...
And go crazy. Take
Yeah,
a
and
reasonable
go-
problem and go crazy.
Go crazy like us.
And sometimes it comes back.
Look, any comment on Lagrangians are just to finish the...
Okay. Well, I mean, there is the issue that we already discussed together since Santa Barbara, right?
Yeah.
That there is it would
Nobody knows Lagrangian analog of fifth. So
it
what
would be
if
nice
there
to know if
exists
one
one?
should expect power rules or not.
And which one? Yeah, that's...
The numerics is very poor. I mean, the signature of power rules from the numerics is very poor. From experiments is even worse. And it remains, I mean, from a phenomenological point of view, zero-order approximation would predict it.
Well, I
But
think
they're not there.
there must be some good idea here. Some need to invent something smart here, because it's clearly a very well-defined problem, and we have no idea. I mean, we're talking about Lagrangian simple particle statistics. How the velocity of Lagrangian particle change with time? What are the statistics of velocity change during time interval? Nobody knows anything. Safe conclusion. 60 years after Obukhov and okay.
Okay, thank you.
Everything's safe.